In this section, you will learn about extrema on an interval. First up, definition of absolute extrema on an interval. Let f be defined on an interval I containing c. Now remember, for f to be defined, that means every x value that you plug in outputs a y value. There's no x values for which the y value does not exist. And the interval I is talking about an x interval, and it contains an x value of c. So first, if f of c is less than or equal to f of x for every x in the interval, then f of c is the absolute minimum of f on that interval. Remember that f of c is a y value, so what this inequality is saying is the y value at c is less than or equal to every other y value on the entire interval. If that's true, then that y value is the absolute minimum. Second, if f of c is greater than or equal to f of x for every x in I, then f of c is the absolute maximum of f on interval I. And it's the same reasoning. If this y value is greater than or equal to all the other y values on the entire interval, then that y value is the absolute maximum of the function on that interval. Now, a couple of notes here. A function may or may not have absolute extreme values on any given interval. So there might be an absolute max, or there might not. There might be an absolute min, or there might not. And just a quick reminder that f of c is the y value, and it gives the value of the min or max, whereas c is the x value, and it gives the location of the min or max. In this example, determine the absolute minimum and absolute maximum, or indicate that they do not exist. In this first diagram, we have to find the absolute max if there is one. We see right here that this y value is bigger than all the other y values on the entire interval. So that satisfies this definition. So then we would say that the absolute max is 2, and it occurs at an x value of 3. So the x value gives the location, the y value tells you what the max is. Now we have to find the absolute min, so the y value that's less than or equal to all the other y values on the entire interval is here. It's -2, and that happens at x equals 0. So remember, the x values tell you where something happens. The y values tell you what it is. Next up, we have this diagram. And to find the absolute max, we look to see if there's a y value that's bigger than all the other y values. And that does happen right here. That y value is 3. And we see that it occurs at x equals 1. So the absolute max equals 3, and the location is that it's at x equals 1. Now for the absolute min, we're looking to see if there's a y value that's smaller than all the other y values on the interval. And in this case, There isn't one. Because there's a hole here, there's not a y value of -1. It gets infinitely close to -1, but any y value you would pick, you could always find a smaller y value that's even closer to -1. So in this case, the absolute minimum does not exist. In this diagram, we are looking for the absolute max, which means we're trying to find a y value that's bigger than all the other y values. And for a similar argument to what we just saw in the previous example here for the minimum, the absolute max does not exist because the function does not attain this y value here at this point because of the hole that's there. Now, it does hit a minimum value here. A y value of -2 is smaller than all the other y values on the entire interval, and that occurs at x equals 2. Extreme value theorem, which we can abbreviate EVT. If f is continuous on a closed interval, a to b, then f has both an absolute minimum and an absolute maximum on the interval. So if the EVT applies, meaning if f is continuous on the closed interval, then the EVT guarantees that there will be a min and a max. In this example, determine whether the graph satisfies the EVT and identify the locations of the absolute extreme values, if they exist, on the interval from a to b. Here we have f of x. Our interval goes from a to b. Now, because f is continuous on the entire interval from a to b, that tells us that the EVT applies. Now, once the EVT applies, it tells us that it's guaranteed that f will have an absolute minimum and an absolute maximum on the interval. Now, on the interval from a to b, we see that the smallest y value happens right here at x equals q, so that means this will be the absolute min. So we can say that the absolute min is at x equals q. Now, in this case, we don't know what the value of that absolute min is because we don't know the y value, but this problem was asking us to identify the locations. Now, the biggest y value in the diagram is here, so this would be the absolute max, and that's happening at x equals a. So the absolute max is at x equals a. And once again, we don't know what the max is, but we know where it occurs. Here we have a graph of g of x. So pause the video and try this one on your own. Then restart when you're ready to check your answer. We can see that on the interval from a to b, that g of x is not continuous at x equals c. And x equals c lies on the interval from A to B. So because G has a discontinuity on the interval, therefore the EVT does not apply. Now that doesn't mean we can't have a min and a max. It just means the min and the max are not guaranteed. And in fact, looking at the diagram, we see that there is a smallest y value. So that means this will be the absolute min. So there is an absolute min at x equals c. And there's no absolute max because there's no y value that G attains that's bigger than all the other y values. So we can say there's no absolute max, or you could say the absolute max does not exist. Either way. Definition of relative extrema. First, if there's an open interval containing C on which f of c is a maximum, then f of c is a relative maximum of f. Or you can say that f has a relative maximum at the point c f of c. Second, if there is an open interval containing C on which f of c is a minimum, then f of c is a relative minimum of f. Or you can say that f has a relative minimum at the point c f of c. Now be reminded that an open interval containing C that means that f must exist on both sides of C. F has to exist to the left of C, and F has to exist to the right of C. In this example, determine if F has any relative or absolute extreme values. Here we have a graph of f of x, and we're trying to decide if there's an absolute max on the graph. Now remember that an absolute max means that the y value is bigger than or equal to all the other y values on the entire interval. Now the interval we are talking about goes from x equals 1 to x equals 6. And clearly, y equals 3 is an absolute max. And it occurs at x equals 2. So this point here is an absolute max. Absolute min, we're looking for the smallest y value that exists on the entire interval, and that happens here. So this is an absolute min, and the absolute min is equal to -1 at x equals 1. Next, we need to decide if there's a relative max. Now, remember, to be a relative max, there has to be an open interval containing C on which f of c is a maximum. If we look at this point right here, we can put an open interval around 2, go up to the graph. F exists for all the x values to the left of 2 and all the x values to the right of 2 on this open interval. And on this open interval here, this y value is the max, so that means this is also a relative max. So the relative max is equal to 3 at x equals 2. Now here, even though this is an absolute min, it is not a relative min. And the reason is, if we put an open interval around x equals 1, we can see that f exists to the right of 1, but f does not exist to the left of 1. There's no function over here. So this is not a relative min, since there is not an open interval of f around x equals 1. So this is an absolute min, because the requirement to be an absolute min is you just have to be the smallest y value there is. And that's certainly true. Y equals -1 is the smallest y value on the whole entire interval. That's why it's an absolute min. It's not a relative min, since we can't make an open interval of f around x equals 1. There's no function over here on the left. Now we do have a relative minimum on the graph, and that happens right here. So this point right here is a relative minimum, and that's because we can make an open interval around x equals 5, and f exists to the left of x equals 5, and f exists to the right. We would be here on this part of the function. So because there's an open interval around x equals 5, on which 0 is the smallest y value, that means we have a relative minimum of 0 at x equals 5. Now this point right here is also not a relative extrema, because once again, there's not an open interval of f around it. So clearly this is not an absolute max or min, because there are y values that are bigger and smaller. It's not a relative max or min, since there's not an open interval of f around x equals 6. So this is just a point on the graph without being an extreme value at all. In this example, given f of x is the absolute value of the quantity x minus 1, sketch the graph and find f prime of 1. Because f of x is the absolute value function, we know we can write it as a piecewise defined function. So it will be the opposite of x minus 1 whenever x minus 1 is less than 0, which is when x is less than 1, and it will be x minus 1 whenever x minus 1 is greater than or equal to 0, which is when x is greater than or equal to 1. Now, if we were to distribute this negative sign here, this is the same as saying negative x plus 1. So when we are graphing this piece of the function, we know to make a line whose slope is negative 1 and whose y-intercept is positive 1. And of course, for this portion, we would have an open circle at x equals 1 because it's not included. Then for x greater than or equal to 1, we have a line whose slope is 1. We know the y-intercept would be negative 1, but we don't plug x equals 0 into this part. We could plug x equals 2 into this part and see that we would get a y value of 1. So graphing this portion, and that would fill in this hole right here. Because if we plug x equals 1 in, we get a 0. So that means we do have the point 1, 0 on the graph. We know that we want to find f prime of 1. But because we have a piecewise defined function, we know that means we should look at the derivative coming in from the left of 1 and the derivative coming in from the right at 1. Now, this top portion is coming in from the left at 1, and that derivative would be negative 1. This bottom piece is the part coming in from the right at 1, and that derivative would be positive 1. So because the derivative from the left at 1 does not equal the derivative from the right at 1, therefore we have to say that f prime of 1 does not exist. Next up, determine if f has any relative extreme values. Now, looking at the graph, we see that we can make an open interval around 1 and on this interval, y equals 0 is the smallest y value. So we have an open interval of f around x equals 1, and on that open interval, the smallest y value is 0. So we have a relative minimum at the point 1, 0. Or we could have said the relative minimum equals 0 at x equals 1. This is an equivalent way to say it. So right here on the graph is a relative minimum. And what I want you to notice right now is at that exact point on the graph, the derivative does not exist. So we had a sharp turn on the graph, and we found that f prime of that x value, which is 1, did not exist. So right now, I just want you to notice that. We had a relative minimum at a point on the graph where the derivative did not exist. So the relative minimum at the point 1, 0 was where f prime of 1 did not exist. So for right now, we're just paying attention to what's happening at those places where we have relative minimums or relative maximums. Given f of x equals sine x, sketch the graph and find f prime of pi over 2 and f prime of 3 pi over 2. For sine of x, we know the 5 key points are that it starts at a root, then at the quarter point, it hits its maximum, so pi over 2, 1, Then it goes back to a root, pi 0. Then it hits the min, 3 pi over 2 negative 1, and ends at a root, 2 pi 0. So we connect up those points. And there's our quick sketch of sine of x. Now, f prime of x is going to be the derivative of sine of x, which is cosine of x. Which means to evaluate f prime of pi over 2, we just have to find the cosine of pi over 2. And looking at the unit circle, we see that that is going to equal 0. And f prime of 3 pi over 2 means we need to do cosine of 3 pi over 2. And we can read that right off the unit circle. It's also 0. Now, if we were to look at the graph, we could actually see that pretty easily as well. At x equals pi over 2, we are at this point on the graph. And we can see that the slope of the tangent there is 0. So f prime of pi over 2 is equal to 0 because we have a horizontal tangent line there. The same is true at 3 pi over 2. The slope of that tangent is also 0. So f prime of 3 pi over 2 is equal to 0 there. Now we have to determine if f has any relative extreme values. And we can see right here, at this point, we could put an open interval around pi over 2. And if we look at that open interval on the graph, y equals 1 is the biggest y value there. So that means this is a relative max. So we can say that f has a relative max at the point pi over 2, 1. Now notice that the value of the derivative there is exactly equal to 0. So where f prime of pi over 2 was equal to 0. Again, we're just trying to notice some facts about what's happening on the graph at the places where there are relative extrema. And at x equals 3 pi over 2, we can make an open interval around that x value. So we get that open interval of f, and we see that on this open interval, y equals negative 1 is the smallest y value, which means this is a relative min. So we can report that f has a relative min at the point 3 pi over 2 negative 1, where f prime at 3 pi over 2 is equal to 0. So what we want to notice is that we had relative extrema occur when the derivative was equal to 0, and in the previous problem, we had a relative extrema occur where the derivative did not exist. So this brings us to the definition of a critical number. Let f be defined at c. Remember, that means if I plug in x equals c to the function, it outputs a y value. F is not undefined at c. If f prime of c equals 0, or f prime of c does not exist, then c is a critical number of the function. As we've observed, relative extrema occur only at critical numbers. If f has a relative minimum or relative maximum at x equals c, then c is a critical number of f. So this means that if there is a relative extreme, you know it occurs at a critical point. So for example, in this graph of f of x, we see that we have a relative min here. And at that relative min, the slope of the tangent is 0, and that means that f prime of 5 was equal to 0. So if we have a relative min at x equals 5, that means x equals 5 is a critical number, and to be a critical number, the derivative is either 0 or does not exist. In this case, the derivative was 0. So we know that x equals 5 is a critical number, and in this case, we did have a relative minimum there. Whereas here, on this graph of g of x, we've got a relative max here, and because of this sharp turn, we know that g prime of 3 does not exist. Remember that critical numbers are anywhere that the derivative of the function is 0 or does not exist. So that means that x equals 3 is a critical number. And in this case, we did have a relative max at our critical number. This statement here, make sure you understand the direction of this conditional statement here. If there's a relative extreme at x equals c, then c is a critical number. But that doesn't work in the reverse. Just because c is a critical number doesn't mean there must be a relative extreme there. So that means not every critical point will have a relative extreme. So for example, if we look at this f of x, we can see the slope of the tangent here is 0. So f prime of 7 is equal to 0, which means x equals 7 is a critical number. However, there's not a relative min or a relative max there. So even though x equals 7 is a critical number, but there's no relative extrema there. So just because you have a critical number doesn't mean you will have relative extrema there. Likewise, if we look at h of x, we know that h is not continuous at x equals 2. And because h is not continuous at x equals 2, therefore h is not differentiable at x equals 2. Remember, we learned earlier that if a function is not continuous at an x value, it will also be not differentiable there. So that means h prime of 2 is undefined, does not exist. So that means we know that x equals 2 is a critical number, but once again, we see that there's no relative extrema there. So what these examples were trying to show you is that if you know you have a relative extreme value, then you know it happens at a critical number. But the reverse is not true. Not every critical point will have a relative extreme value there. It's possible to have a critical number, as we did here and here, but there's no relative extrema there. Next up, you learn a method for finding absolute extrema on a closed interval. Consider a continuous function, f, on the closed interval from a to b. Step 1, find the critical numbers of f in the open interval from a to b. Step 2, evaluate f at each critical number in that open interval, a to b. 3, evaluate the endpoints, f of a and f of b. And in step 4, the smallest y value that you found in steps 2 and 3 will be the absolute min, and the largest y value that you found in steps 2 and 3 will be the absolute max. Let's work through this example where you have to find the absolute extreme values of f of x equals x to the fourth minus 2x cubed on the interval from -2 to 4. So step 1 tells us to find the critical numbers of f in the open interval, in our case, from -2 to 4. We know that critical numbers occur when the derivative of the function is either 0 or does not exist. So then to find the critical numbers for this f of x, we need to take the derivative, f prime of x, that's an easy one, 4x cubed minus 6x squared. Let's go ahead and factor this. We can pull out 2x squared, and we would take that times 2x minus 3. And now we need to find the places where the derivative is either 0 or does not exist. So we will take this and set it equal to 0 or undefined. Now this expression will equal 0 whenever x is 0. That comes from this first factor. From the second factor, that will equal 0 whenever x is equal to 3/2. And we got that by setting 2x minus 3 to 0 and solving for x. Now, a polynomial is never undefined, so it's never going to be a DNE. So then that means x equals 0 and x equals 3/2 are the critical numbers. Now step 2 says evaluate f at each critical number. So when we evaluate f at each critical number, that means we need to do f of 0 That's always our favorite number to plug in. Remember, we're plugging into the function, not the derivative here. So that would be 0 to the 4th minus 2 times 0 cubed, which of course is 0. We also have to evaluate f of 3/2. So that will be 3/2 to the 4th minus 2 times 3/2 cubed. Now, when I have to do this, and I'm not using a calculator, I see that I have a 3/2 to the 4th here and a 3/2 cubed. So what I would do is factor out that 3/2 cubed, because that's going to be easy to evaluate. And then from this first term, we would have 3/2 left minus, from the second term, we just have 2. So now this is going to be pretty easy to evaluate. Here we have to do 3 cubed, which is 27, over 2 cubed, which is 8. And we have to take that times 3/2 minus 4/2, which would be negative 1/2. So this was easy to do without a calculator, and we end up with negative 27 over 16. Step 3 says we have to evaluate f at the end points. So that means we need f of negative 2, which is going to be negative 2 to the 4th minus 2 times negative 2 cubed. Negative 2 to the 4th is 16, and we have to subtract 2 times negative 2 cubed. Well, negative 2 cubed is negative 8 times negative 2 turns that into positive 16. So f of negative 2 equals 32. The other endpoint is x equals 4. So we have to evaluate f of 4. That would be 4 to the 4th minus 2 times 4 cubed. And once again, if I'm doing this without a calculator, I probably would factor out that 4 cubed, and then I would have 4 minus 2 left, just because it keeps the arithmetic a little easier. 4 times 4 is 16, times 4 would be 64, and then we just have to take that times 4 minus 2, which is 2. So this is 128. In step 4, we take the smallest y value and make that our absolute minimum. We had a y value of 0, a y value of negative 27 over 16, a y value of 32, and a y value of 128. The smallest is this negative 27 over 16, so our absolute min is equal to negative 27 over 16, and it's at x equals 3/2. So that's the absolute min. The largest y value will be the absolute max, and that's this 128. So the absolute max is equal to 128, and that occurs at x equals 4. And notice that in this case, the absolute min occurred at x equals 3/2, which was one of our critical numbers, whereas the absolute max occurred at x equals 4, which happened to be one of the endpoints. That's why you have to look at all the y values from the critical numbers and all the y values from the endpoints and make the smallest one the min, the largest one the max. Find the absolute extreme values of f of x equals 2x over the quantity x squared plus 1 on the interval from -2 to 2. Now, step 1 tells us to find the critical numbers of f. We know that in order to do that, we have to take f prime and set it equal to 0 or does not exist. So let's first find this derivative, f prime of x. Because f is a quotient, we are going to have to use the quotient rule. The quotient rule, of course, is f prime g minus f g prime over g squared. So we have to take the derivative of the top, which would be 2, times g in the denominator, x squared plus 1. Then we have this subtraction symbol, and we have to take f, which is 2x, times the derivative of the denominator, which would be 2x. That whole thing is over g squared, so we take this denominator and square it. X squared plus 1, quantity squared. Now let's simplify. In the numerator, when we distribute this 2, we would get 2x squared plus 2. Then from this second term, we would get minus 4x squared over x squared plus 1 quantity squared in the denominator. Now this is going to equal, let's combine like terms, 2x squared minus 4x squared means we have a negative 2x squared plus 2 over the quantity x squared plus 1 squared in the denominator. Now we can factor out a negative 2 from this numerator. So we have negative 2 times the quantity x squared minus 1, and that's over the quantity x squared plus 1 squared in the denominator. So we can simplify this a bit more because we know that x squared minus 1 is the difference of two squares, and we can factor it. So this becomes negative 2 times x plus 1 times x minus 1 in the numerator over that same denominator, quantity x squared plus 1 squared. And this is our f prime of x. Now, to find the critical numbers, we have to find the x values for which f prime of x equals 0 or does not exist. We know that a rational function will equal 0 whenever its numerator is 0 and its denominator is not 0. And at x equals negative 1, that happens, because if we put a negative 1 here, we get 0, but if we put a negative 1 down here, we don't get 0. This also happens at x equals positive 1. The numerator is 0, and the denominator is not. A rational expression will be undefined whenever its denominator equals 0, and since x squared plus 1 will never be 0, this will never happen. So that means we have two critical numbers, x equals -1 and x equals +1. Step 2 says to evaluate f at each critical number. So we have to find f of -1. Remember, we are plugging into the function, not the derivative. So that's going to be 2 times -1 over -1 squared plus 1. So that simplifies to -2 over +2, which equals -1. The other critical number is x equals 1, so we have to do f of 1, which would be 2 times 1 in the numerator over 1 squared plus 1 in the denominator. So this is 2 over 2, which equals +1. Step 3 says to evaluate f at the endpoints. So f of -2 is going to be 2 times -2 over -2 squared plus 1. So we get -4 in the numerator and 5 in the denominator. And the other endpoint is x equals 2, so we have to do f of 2. We've got 2 times 2 in the numerator over 2 squared plus 1 in the denominator, so that will work out to be +4/5. And in step 4, we know the smallest y value of these four will be the absolute min. So the smallest is y equals -1, so that means the absolute min is equal to -1, and of course that occurs at x equals -1. And the largest y value will be the absolute max, and that turns out to be y equals 1. So the absolute max is equal to 1, and that occurs at x equals 1. So in this case, both the absolute min and the absolute max happened at the critical numbers. That's not always the case. Here we have to find the absolute extreme values of f of x equals x minus 3x to the 2/3 on the interval -8 to 64. We know step 1 is to find the critical numbers of f, and to do that, we have to find the derivative and then set it equal to 0 or does not exist. So f prime is going to equal the derivative of x, which is 1, minus 3 times the derivative of x to the 2/3, which would be 2/3 x to the 2/3 minus 1, which is -1/3. So simplifying, we have 1 minus, these 3's will cancel, and we would have 2 times x to the -1/3, or we can write that as 2 over the cube root of x. Now we need to get a common denominator, which of course will be cube root of x. So this becomes cube root of x minus 2. We put that whole thing over cube root of x. So from here to here, all we did was get a common denominator. Now to find the critical numbers, we have to find the x values where the derivative is either 0 or does not exist. Because we have a rational expression here, we know to get 0, we need the numerator to be 0 and the denominator to not be 0 at that x value. To get 0 in the numerator, we need cube root of x minus 2 to equal 0. Well, that will happen when x is equal to 8. And that's because solving cube root of x minus 2 equals 0 means cube root of x equals 2. If we cube both sides, we end up with x equals 8. And for this rational expression to be undefined, we need the denominator to be 0, and that will happen at x equals 0. So we have two critical numbers here. And next up, we need to evaluate f at those critical numbers. So evaluating f at 8, which was one of our critical numbers, we know that we have to do 8 minus 3 times 8 to the 2/3 power. So that's going to be 8 minus 3 times. Now we can do the cube root first. The cube root of 8 is 2. 2 squared is 4. So this just becomes 8 minus 12, which is negative 4. Evaluating f at the other critical number, which was 0, then we would have 0 minus 3 times 0 to the 2/3, which of course is 0. Then we have to evaluate f at the endpoints. So that means we have to do f of negative 8. And that's going to be negative 8 minus 3 times negative 8 to the 2/3. So that becomes negative 8 minus 3 times. Now the cube root of negative 8 is negative 2, and then negative 2 squared is going to be 4. So we have negative 8 minus 12, which is negative 20. And then f of the other endpoint, which is 64, is going to be 64 minus 3 times 64 to the 2/3, which is going to equal 64 minus 3 times the cube root of 64 is 4, and then 4 squared is 16. So we have 64 minus 48, which is 16. And then in step 4, the smallest y value will be our absolute min. Of these 4 possibilities, the smallest one is negative 20. So our absolute min is going to equal negative 20, and that happened at one of the endpoints, x equals negative 8. The largest y value will be the absolute max, and of these 4 choices, The largest is 16, so the absolute max is equal to 16, and that occurred at x equals 64, which was the other endpoint. So in this case, both the absolute min and the absolute max happen to come from the endpoints. And as you saw in these three different examples, they can both come from the critical numbers, they can both come from the endpoints, or you can get one from each. That's why you just have to plug in the critical numbers to F, you have to plug in the endpoints to F, and then you see which are the largest and smallest y values.